thanks for having me here. Indeed, I'm program manager of imec spectral imaging on chip activity. And today I prepared a preparation showing the work or how our technology can make a difference for biomedical imaging. And I picked presentations, or I picked applications and examples that focus more on the microscopy part. I'm not so in-depth familiar with biological imaging or with biomedical applications. I have a background in physics, but I hope to inspire with what we have done so far with our technology, or what our customers have done with it, and by trying to explain how our technology works. So to start off, maybe a few words on imec. So imec is an R&D center in Leuven, Belgium, that was founded in '84 for researching transistor downscaling, hunting down Moore's law, and since then it has evolved in a general R&D center for anything silicon technology based in researching. The main activity of imec is still researching for transistor downscaling. So today we are developing the EUV tools together with, for instance, TSMC and other leading industry companies. And that's about 50% of our activity. And we have the luxury that around 2000, we had to invest in a new clean room, and they decided to use the 200mm clean room, which is here on my slide, to investigation to more and more. So thinking about initially MEMS, LEDs, photovoltaics, but today also microfluidics, silicon photonics, and so on. And one of these technologies is hyperspectral imaging. So that unique infrastructure of imec enables a lot of very interesting research. We have 5,000 R&D engineers working at imec on multiple sites across the world. imec Leuven is the headquarters, but there's a large part also in Eindhoven in the Netherlands, also at One Planet in Wageningen and Orlando, USA, and then there's also sales offices around as well. And then our goal at imec is to develop new technology and find foot on ground in industry for these technologies. So, and that's the same with hyperspectral imaging. So one thing on hyperspectral imaging, just to make sure everyone can follow. So one thing is point spectroscopy, where we would be looking at one specific point on a sample or on a heterogeneous homogeneous sample and measure a spectrum in all its detail over a wavelength range. So that is showing how a sample is reacting, for instance, in this case, atmospheric absorption with light. So as you know, some wavelengths don't pass through the wavelength through the atmosphere, and others pass very well. So enabling very accurate spectral analysis, but only on one location or on a homogeneous mixture. Then at the other hand, we all know our family pictures, which are made by a RGB sensor, which is in our smartphones or DSLR, which is actually capturing colors, but making an enormous generalization of colors, saying this chunk of this wavelength spectrum, we call it blue, this chunk we call it green, and that chunk we call it red. But at least it makes a nice picture that our eyes can interpret as true, very similar to the truth. If we go to holidays, we come home, we want to have an impression that gives us something. Now, spectral imaging is combining both worlds. It's trying to have a spatial information while preserving sufficient details in discretizing the spectral domain. So, spectral imaging enables to capture an image with spatial information, enabling to tell something about a heterogeneous environment, and also capture at the same time material properties or the way materials in that environment interact with light. So as a very brief summary. So what is our approach to spectral imaging? Because in fact, spectral imaging is not so new at all. Spectral imaging has been around even before digital sensors existed. But what is apparent to spectral imaging is that all this time it has been realized by combining optical components in multiple different fashions. And there's, I think, dozens of approaches to split light in its facets and capture a spectral signature. But typically it's an implementation of optical components that will be splitting the light in its different wavelengths in between a focusing objective and a detector. And the consequence of that is that not only devices become quite bulky, they are also typically not so straightforward to make. There's a lot of components that need to be aligned to each other, which means that over time they can misalign, they need recalibration, but also it's not a very scalable approach to making devices. And so that's where our technology can make a difference. In fact, what we have realized, and that's not something from yesterday, that's something we have realized over the course of the last 10 years, is the implementation of spectral filters directly patterned at wafer level on an imager chip. And what this means is that on an existing, so actually maybe for people that are not familiar with CMOS processes, so electronics are developed on a wafer, and what we are seeing here is, apart from the colorful these rainbow patterns, every rectangle on this wafer is an individual imaging die or chip before it is being cut into pieces and integrated in a package. So what we are adding at imec is the spectral filters or color filters as thin film filters and patterns on an individual pixel of that chip, so that after packaging, this traditional imaging chip, instead of being a black and white chip or a panchromatic chip, it will become a hyperspectral chip. And the important thing in that is that we did not change in any way the electronics. So if a camera was compatible with a certain imaging chip before our process, it will also be compatible after the process, leading to the fact that with this technology, we can make spectral imaging systems that are very miniaturizable. We can also do this in a CMOS, so consumer electronics oriented production fashion. So it can also be scalable in volume, scalable in price. And what I like actually most is that the camera is just a camera. So whereas normally spectral imaging systems and system level implementation become quite difficult to integrate with other imaging devices, like with a microscopy system or a fundus microscope or a traditional microscope in reflectance or transmission or a surgical microscope. Here, this is a C-mount, a camera with a C-mount, which can be directly mounted on the C-mount of your optical instrument. And so it looks like a camera, it smells like a camera, and it's actually just a camera that you mount a lens on it. So it's really really easy to integrate them at application level as well. And today we have developed this technology in the visual light range, so 400 to 700, near infrared 700 to 1000 nanometers, and also in shortwave infrared, which we call 1000 to 1700 nanometers. So, and one thing that I also would want to focus on is not only be miniaturized, but that brought us over the recent years a very important capability. And in fact, that being that we can pattern these small structures on a single pixel level. So we get to choose on which individual pixel we put which kind of resonance filter. And so we can think about something similar to a Bayer pattern, however, with narrowband spectral filters. And the true power of that is that this is for the very first time enabling a true snapshot acquisition and thus video rate spectral imaging. As is demonstrated here in this video cast from our software in a demo studio, we are here recording live imagery where each individual image is acquired in one snapshot. So there's no time multiplexing to acquire the spatial spectral information, and recording that at a certain frame rate. we are getting on this scene the variability or the changes, dynamic changes in the spectral contents depending on where it happens, and we can use that information for a real-time classification just based on material properties. So this is very different from traditional spectral imaging, and it's enabling a ton of new applications where primarily we would be focusing on scenes where there is an inherent motion in the scene, or where there's an uncontrollable motion between the imaging device and the scene. So for instance, then scenes with inherent motion, as I will illustrate, for instance, retinal imaging, also surgical imaging, live cell tracking, dynamic process monitoring, or even also in agriculture, there's many applications where there is wind blowing through the fields, causing dynamics in the field. And then where there's a non-controlled motion between the camera and the scene, we can immediately think about handhelds in the form of for in-field applications, for industrial inspections, but also for laparoscopic cameras or surgical cameras. And that is where I believe we can make a real difference, apart, of course, of the downscaling capabilities and the scalability and volume. Now, the challenge, spectral imaging is an imaging modality. There's really many things you can do with it. So today, our customers are using our technology from industrial machine vision over security applications to monitor gas leaks or oil leaks on piping installations, on new space for CubeSats with our chips, which is very convenient because of, again, the small form factor, to environmental monitoring, microplastics detection, agriculture, and then, of course, also biomedical, maybe today's largest application domain. And there, the range can go all the way from very small implementations in endoscopes, but it can also go to very large scientific CMOS detectors with large sensitive pixels with a high full well capacity to do fluorescence imaging on microscopy and others. So here's also that overview in one slide, and there are imagers in space. There are farmers using them. The other day, we're talking to surgeons and medical practitioners, which makes our job actually really interesting because we are confronted with so many different application fields. Now, I won't bother you today with the fruit disease detection in early stage, but let's zoom in what we can do in the biomedical sector. And one of the first applications I want to highlight is the compatibility or integration of our technology on a fundus microscope. So here we are in the ophthalmologic department, where the medical doctor is looking to form an image of the retina, and the idea is there that the retina is exposing directly a very large bundle of nerves at the surface of our eye, so it can serve as a window to the brain. And as from that, the idea behind is that if there are processes happening in the brain, if there are certain proteins forming in the brain, then if they are residing in your brain, the chance is probably quite large that through this connection directly to the back of your eye, these proteins will also be present in that area. And so this was investigated together with UZ Leuven, Vito, and us to see how can we mount this spectral camera on this instrument. And so we effectively succeeded to mount this camera on a C-mount adapter of the Topcon TRC fundus microscope, and synchronize the trigger of this device with the acquisition, and have an instantaneous snapshot acquisition of the back of the eye, providing spectrospatial information for later post-processing. And what's more is that we were capable, well, not imec, but Vito and UZ Leuven were capable of developing the AI required to pick up the signature of beta amyloid, which is the plaques that are a biomarker for Alzheimer's disease in a patient. And what's more is that this enables even a very early stage of detection without having to do a puncture of bone marrow or find the presence of these plaques in the blood. So this is a very nice demonstration of applying spectral imaging to pick up a spectral signature of a protein in the eye. So today this is being further developed, not only by UZ Leuven, but by also different startups across the world. And the hope is that the same can be done as well for Parkinson's disease and many other diseases, also in the field of cardiological diseases. So then, now we've been looking at snapshot, but one other system that we have developed that I think is very interesting for biomedical research and microscopy applications is where we are combining our line scan implementation of the filters in a SnapScan type of system. So with line scan, what we'll be doing differently versus the Bayer pattern is, instead of making a Bayer pattern that's repeating itself all over the area of the imager, we will be putting stripes of different spectral bands or different spectral filters over the width of a sensor. So we will be splitting the image that is projected on the sensor in different wavelengths. So then we can, normally by translating an object relatively to the camera, you will form an image or a scan that will yield a high resolution. The challenge is in that you need some translation mechanism. You need to synchronize the translation with your acquisition. You need to also have a perfect alignment between the motion plane and your acquisition plane, and that's a lot of hurdles to tackle if in the end all you want is good imagery to start your application research. So what we have developed is a camera that will be doing a translation internally, making that this camera is looking at the scene with 3D geometry. And here you can also think about, for instance, biopsies on a microscopy slide, which also have this 3D structure. And the lens or the optical system is making a projection inside of the camera of this 3D scene. And then what we will be doing is, by translating the sensor inside of the camera, we'll be acquiring a few hundreds of images at very synchronized moments or very synchronized positions of the sensor in the camera, and we will be obtaining a very high resolution spectral imaging data cube. And with very high, I mean 7 megapixels per spectral band with 150 spectral bands, for instance. Also in short-wave infrared, although the resolution is a bit lower there because of the sensor constraints, there we will have unseen resolutions of 1 megapixel per band with 100 spectral bands. And this in a convenient way of a point and scan fashion. So there's no external synchronization required. So as an example, what this can mean, and there probably the experts will see that we are not the application experts. We just took a slide that we found interesting. So this is red and white blood cells. And what we have done is, here we have a 7 megapixel color reconstructed image. And behind every pixel in that image, there are 150 spectral samples. And that information can then be used to do a classification purely based on the spectral information, spectral differences between the different structures in there to tell where is which kind of particle. So our customers have then also adopted this kind of implementation and are today scanning slides of pathologists and with pathologic examination and information. For instance, in this case, a slide of lung tissue, where the interest of the application is to detect the lung, where there's presence of lung cancer or markers indicating lung cancer. The dream in that case is to go to unstained sample scanning and to pick up the absorptions of the compounds present in the tissue to identify, typically in healthy tissue, that is the kind of mixture you would find of the different compounds forming cell structure and yeah, the content in there. And so this is an alien tissue type to what we would expect in this slide. The application there is that if such a high throughput device could be made with this technology, it would help tremendously to guide the pathologist to look at which slice need his attention and which don't. So optimizing optimizing the time spent of a pathologist tremendously. And then a third application where I want to zoom in is the integration also on surgical microscopy instruments. So very first, and I see I forgot the reference, for which I apologize. The very first demonstration of this with one of our very first cameras was done by Pichette at Polytechnique Montreal, where they integrated the snapshot Viz sensor on the surgical microscope. And the idea there was that if we look at the absorption peak of blood and blood without oxygen, so oxygenated blood versus disoxygenated blood, there is a sharp difference at specific wavelengths, and there are multiple crossing points. So there is hope that with capturing a spectral signature in that range, there you could pick up the signature of these two types of blood and in different concentrations to tell where is blood with oxygen, where is blood without oxygen, and how is that dynamically evolving. And this is effectively what they demonstrated. So not only there's distribution of and displacement of blood with oxygen, there is also blood volume measurements possible. And the hope in this study, or the goal, was to correlate that with eventual epileptic attacks of the patient under study. Now, this is the very first realization looking at blood volume and blood oxygen content in a qualitative way. So today, this research has been repeated and improved over and over again. For instance, by Linköping University or DKFZ Heidelberg, who are integrating that on a laparoscopic setup, doing quantitative real-time measurements of blood and blood volume to monitor organ ischemia. And what we are working on beyond that is now pushing the boundary beyond this application. We want to also start looking at not only critical structure identification, but we have done research together with UZ Leuven and Zeiss, integrating our SnapScan camera on the Zeiss Pentero microscope. And on the very initial results of this clinical study, we were able to prove that with only hyperspectral data, it is possible to train an AI to detect today with 80% detection accuracy which tissue is healthy versus which tissue is low-grade glioma. And what is important in this is that, even though very preliminary, this the algorithm manages to filter out that information from the spectral data, while even a trained surgeon has a hard time to tell the presence of low-grade glioma in just by his eyes. So there today the struggle was to do an accurate surgical navigation and tracking to map the preparation on the actual situation in the scene, in the surgical scene. So there is hope that our technology can contribute to having a real-time assisted surgery input during the operation. So this is these are 3 selected applications I wanted to highlight today to scope a bit the application domain that is being investigated with our technology within biomedical imaging. So now probably one of the questions is, of course, if we are making a wafer level technology, how can we bring this to market? And so we, as a technology center, we rely a lot on academia, the research world, R&D centers, and also R&D divisions of companies to further the adoption of our technology. So for that, we have also developed an off-the-shelf offering, where we have, for instance, developed sensors, both in snapshot and also scanning mode, with several different bands from vis all the way to shortwave infrared. And because many people, when they hear they can buy a sensor, will still be clueless, we also set up partnerships with companies such as Zimea, Photon Focus, and others to get access to this technology in camera. So what is our contribution to that, beside the sensor, is that we also provide all the software that is required to start using these cameras, so that as an application specialist, you don't need to become a spectral imaging specialist before you can actually get data. Our goal is to make it as easy as possible, so that you can get started with application research as soon as possible, and without more. Of course, if people contact our support to know more about technology, we are always very happy to explain them more. And then in the end, our goal is, of course, to customize the technology. And there we also have the capability to engage with our customers, connecting really to their application, to the specifications of what they need to make the implementation of our technology fit to the volume value of their application. In conclusion, we have a technology that is that I believe can enable many new applications that were previously, with other implementation of spectral imaging, not accessible. We are looking as a research center to find foot on ground for these technologies in various different application spaces. Today, biomedical imaging is maybe one of the most promising domains forward, but we need a lot of help and feedback from the community. For that, we are taking a very open position to help researchers and companies to adopt and evaluate technology. And there is a perspective to industrialization on the longer term. So with that, I hope to inspire, trigger some ideas, and I wish to thank you all for your attention and having me here again on this event.